right, so the next thing I want to talk about is exponential growth. Or natural growth when you have unlimited resources. Okay. So let's just say you have a giant tank filled with lots of nutrients so that germs can easily divide. And you initially have some germs put in. Let's say that the initial population of the germs is P. So P of T is germ population at time T. And what we want to model is how would this germ population grow with respect to time. And here's how you make the model. See, germs, they grow by dividing, right? Of course, there's a rate of division which we don't know, so that part we have to figure out by experiment. But certainly, we can predict that the more germs there are, the rate of change of the, or the growth rate of the germs will be big. Okay, so if this is, you have a large population, it's going to be growing faster compared to the case when you have a small population, right? So you can write down the equation in this way. The rate of change of the population with respect to time is proportional to how much population you already have. This symbol means it's proportional. Okay. Now, if you have two quantities proportional to each other, then there's a way to turn this into an equation. How do you do that? You write down a k, proportionally constant. You can put some other number. Usually people write k or lambda or something, times p. So you just set the left side equal to some constant k times p, where k has to be determined afterwards. Now, how do you solve such a thing? Well, here's the problem with such an equation. See, now you can't really integrate both sides. Let me show you what happens if you try to integrate both sides. If you try to integrate both sides, the left side is okay. What do you get if you integrate the left side? What's dp dt? What does dp dt mean? You've differentiated p by t, right? And then you're integrating by t. What does that mean?
You get p.
Huh? You get p. You get your p back, right? So if you integrate what you differentiated, you get p. That's easy. However, on the right side, you're trying to integrate this function pt, but I don't know what p of t is. If we knew that, we wouldn't even try to solve this differential equation. So it doesn't make any sense at all. So you can already see that even simple differential equations like this require something more than just regular integration. So direct integration wouldn't be able to solve this differential equation. All right, if direct integration fails, then what do you do? Well, know who first thought about this, but this is what this is how you solve it. You divide by p, so you get 1 over p dp dt equal to k. So I divide by p both sides, so this will be divided by p, or 1 over p is multiplied on the left side. And this p will be gone because you divided it. And then you're trying to integrate both sides by dt. Okay, the right side now is easy to integrate. What's this? What's the integral of the right side? kt plus c. What about the left side? Do you know how to integrate this? I'm curious to know if anybody can. Yes?
Is 1 over p just a constant right there?
No, p is a function of t.
Oh.
Yeah. So you're right. If 1 over p was a constant, you can pull it outside and then you just have p again, but that's not what it is. It's, they're both functions of t. Okay, so let's try this. Take u as p. I'm trying to do u substitution. Okay. Keep in mind that when I say this, p, because p is a function of t, I'm really saying u, which is a function of t, is this function. But usually, because when you do u substitution, you just use u, so I'll write it this way. Okay, then what is du? What's du? Looks like I'm going to have a lot of trouble this semester. Wow, this is easy. What do you get? Yes?
dp.
What?
dp.
Okay, I agree. Yeah, it's dp, but usually when you have something like u equals x squared, what do? Du is?
2x.
2x dx. That's what you do, right? Where did you get this 2x? You differentiated this, right? So if you follow the same reasoning, du is?
1/2 p.
Huh? What?
One.
No.
P prime of t.
P prime of t, thank you. P prime of t dt. All right. Okay, and because this is really p prime, here's what we have. This becomes now 1 over p is 1 over u. And p prime dt is just du. Is that right? So this is p prime times dt, p prime times dt, so that can be replaced by du. And 1 over p is 1 over u. Good? Yes? What's the integral of 1 over u?
ln of u.
ln of the denominator. Plus. Well, you only need to put c on one side, so that's good enough. And because u is equal to p of t, I can replace p of t back in there. So that's what we get. So we know that the left side becomes p of t. Now, let me show you a shortcut. And by the way, this will be always the way that we're going to do. So instead of doing the u substitution, this is equivalent to the following. You can just right away cancel the dt here and there. And then what is it? 1 over p dp. What's that? It's ln of p of t, right? Isn't this, if you have integral of p dp, 1 over p dp, that is indeed ln of p, right? So we get the same thing. So we could have done it that way, right? but in fact, what's happening here from here to there is U substitution. That's what I want to say. That's why I want to spell out everything. Okay? All right, so whatever you do, you're going to get ln of p of t on the left side equals to kt plus c. And to get rid of ln, you take e both sides so that they cancel. And we're almost there. And by the way, we'll just assume that p of t is always positive, so you don't need the absolute value. Population is always positive, right? So we have p of t equals to e to the kt plus c. Now we're going to do another transformation of this function on the right side. And that's something that we're going to do frequently, so you should take note of what I'm doing here. This is this can be written as e to the kt times e to the c. Okay? That's the addition rule for exponents, right? If you have two exponents with the same base, then the exponents add up. I'm applying that rule backwards. And then think about what this is. This is some constant, c is some constant, so e to c is some constant, right? So rather than writing it in this way, why not just rename this as something like e tilde? No, c tilde, sorry. Rename this as some c tilde. I mean, I don't care what this e to c is. It's just some number, okay? So I'm just going to call it as c tilde. So this is what I have. And in the final form, I can even drop this tilde and say, let's just say, in turn, maybe we want to call this as tilde, and maybe we want to call this as that as c. That's cleaner, right? So in the final form, we don't have to explain ourselves why that tilde is there. So what we see is that this model for germ population has a simple solution, which is population is an exponential function times some constant. And because we have two undetermined constants, we will need two data points. All right, although we have only 5 minutes, let me quickly give you an example where this can be applied. So, example, at noon, bacteria culture of size 1,000 was put into a tank. At 2 p.m., there were 2,000 germs or bacteria. Bacteria is already a plural, right? Bacterium is a singular. Right? So 2,000 bacteria. Okay, and then question is, at what time will there be 1 million bacteria? Question? And we'll solve this question assuming that we already have this solution. See, ideally what we need to do is we have to start from this one. Let's actually write down what we need to have. So dPet equals to k times p. That's the differential equation we have to solve. And p of 0 is 1,000. and P of 2 is 2,000. Those are the conditions given, right? So at noon, if you call it time 0, this is what we have. If you call 2 p.m. as 2 hours, so our unit for time is hours, as 2,000. The question is, for what t is 1 million? That's the question. All right. So we'll skip the part having to solve this differential equation and just use this one. So let's try to use this. So P of t is equal to c times e to the kt. P of 0 is 1,000. And if you plug in t equal to 0 here, it's c to the e to the 0th power. Anything to the 0th power is 1, so you just have c. So that means c is equal to 1,000. And then P of 2 being 2,000. If you put 2 here, that's 1,000 times e to the k times 2. Divide by 1,000, so 2 is equal to e to the k times 2. That's ln of 2 equals to 2k. So k is equal to 1 over 2 ln of 2. So I have c and k. Putting it back, I now fully know what P of t is. This is 1,000 times e to the 1/2 ln of 2 times t. That's what P of t is. And now all I have to do is figure out when this reaches 1 million. So we have to solve this for t. Let's do that. Divide by 1,000. So that the right side becomes 1,000. To get rid of ln, to get rid of e, we take the ln. And then now, finally, I divide this to the right side, and we get t equals to 2 times ln of 1,000 over ln of 2. And this is, I mean, you'll need to use a calculator to figure this out, but I know that 2 to the 10th power is about 10,024. So this is about 10, so it's about 20 hours from noon. So let's see, 12. So on the following morning, 8 a.m., you'll be seeing about 1 million bacteria in the tank. That's what you figure out. Okay. That's all we have for today.